Inverse functions. Tell me what you know about inverse functions. No, we've heard enough out of you. No, let's hear from somebody else. Like Ella. Ella, what do you know about inverse functions?
We did them in pre-calc.
I'm sorry?
we did them in pre-calc.
Okay, that's something that you know about them. Good.
Is it like the functions where you have like, it's f of x equals something and then it's like f negative? Like, do you know what I'm talking about? Like the little negative sign and then of x?
Yeah, that's the notation.
That's all I remember.
Yeah, you're right. The notation for an inverse function is f raised to the negative first power. Not to be confused with the reciprocal, but yeah, that's the way that we express an inverse function. So you have f prime, f double prime, f triple prime, f to the negative first, which is the inverse. Okay, good. Anything else? Do you know how to find an inverse function?
No, I don't remember.
Suppose I give you the function the square root of x. What's the inverse function of the square root of x? Anybody? John?
X squared,
Why?
because it would undo it.
Yeah, there are functions that undo each other. So, all right, Alice, so if I give you addition, the inverse function of addition is subtraction and division is multiplication, and then we put those things together and we get a big function. Do you remember how to find the inverse, though? If I give you a more complicated function, you remember how to do that? Okay, well, I'll remind you then, because I got it in here. All right, that's not a bad start. We're going to talk about determining if two functions are inverses of each other. So here's a function f, here's a function g. Is it possible that those are inverses of each other? Instead of here's f, go find its inverse, we're not going to do a lot of that, a little bit. We're going to test functions to see if they are. This is a common terminology, and I'll admit early on that I will slip into this, but all functions have inverses. It doesn't matter how complicated the function is, you can find the inverse of a function. The question is whether or not that inverse is a function. So you'll hear that the difference in the terminology is finding an inverse versus finding an inverse function. We're concerned about inverse functions. However, I will admit I slip and I just use the term inverse. What I mean by inverse is inverse function. Does that make sense? Mm-hmm. So you can take a function, find the inverse. That inverse might not be a function. We're looking for inverse functions. Okay. And this is the calculus then. We're going to find the derivative of that function. There are two ways to do it. I'll show you both, but I'll show you stress the easier way. And the easier way involves some geometry and some simple graphing. Okay. And then just be nice to people. Okay. Or don't. So here's the notation Ella was talking about, f to the negative first power. So those two things are inverses. And then we've got the old pictures of the functions here. That we take one function, we move to the other, and then we take the other function. When you go backwards, that's what the inverse is. And so we start with a bunch of numbers, you do something to it, and you get another bunch of numbers. So you go from the yellow to the green. Whether that function is, let's say, squaring. You know, put 2 into the function machine, it spits out 4. But then if we want to go backwards, it's undoing what we've already done, which is how we define that inverse. Down at the bottom there is an important little tidbit of information that we're going to use quite a bit, and that is the domain of the stuff in the yellow is equal to the range of the stuff in the green. And the range of the stuff in the yellow is equal to the domain of the stuff in the green. So there are times where I might ask you to find the range of, let's say, the yellow function, and that's some ugly math. So an alternative way to find it would be to find the domain of the green function, or the inverse. And then maybe I'm kidney stone problems.
Okay.
So you're good.
Yeah, I'm good.
All right, good.
Till next week.
Yeah, he's not here Tuesday. Okay, then the other thing on this slide is this business here. If we want to check to see if two functions are inverses of each other, use a composite function. Put one function into the other, see what you get, and then do the reverse. If they both give you x, then they're inverses of each other. And you have to check both. Okay, so here's two functions, f and g. I'd like to know if those are inverse functions. And right off the bat, things look pretty good. I've got a 2 and a 1 in f of x. I've got a cubic function. In g of x, I've got a cubic root function. Still have the 2 and the 1, so there's probably a pretty good chance that those are going to be inverses of each other. So let's do the work. Change this. So I need to find first what's f of g of x. And then over here, I need to find g of f of x. And these puppies will be inverses of each other if they turn out to be both equal to x. So I'm going to put g into f, which means 2 times the cubic root x plus 1 divided by 2 quantity cubed minus 1. Excuse me. And I think you can all see, you're very bright mathematically. You cube a cubic root, it cancels. Multiply by 2, divide by 2 cancels. 1 minus 1 is 0, and sure enough, kablam, x. Not sufficient. You need to check both. Most of the time they'll work out just fine, but there are bizarre functions out there where it might not work. So the cubic root of 2x cubed minus 1 plus 1 all over 2. And again, you can see quickly that negative 1 plus 1 goes away, 2 divided by 2 goes away, the cubic root of x cubed is x, and we're good to go. Question in the back.
Is the changing y's and x's not a valid way of doing it anymore?
That's,
Well, that doesn't.
that
prove it
does
or
something
inverse.
different.
That
That finds
finds
the
you the
function.
inverse.
I'm checking to see if these
Okay.
functions, that we're getting to that.
Yeah, because you could have just done it. And but if you were to find that the inverse of 2x cubed minus 1 was the other function, you have to go back the other way, right? To
Correct.
prove it. Okay.
Yeah, so it's easier to do two composite functions, I think, than to find the inverse. We good? This picture is very important. So the dark black line is 2x cubed minus 1. The light gray line is the cubic root of x plus 1 over 2. They are inverses of each other. We established that already. But when you look at it graphically, one of the things that I don't even know if you talked about last year, I hope you did, is that inverses are reflections of each other over the line y equals x. Does that sound familiar at all? Okay, good. And that's an important point that we're going to need for the calculus that I'm going to show you later. Let's suppose I've got a point on this function here. Let's call it a comma b. Okay, so that's on the original function. Question in the back.
Would they ever reflect over any other line except for y equals x?
No, it's always y equals x.
Okay.
Yeah. So it's got that 45-degree fold thing going on. Okay, so I've got this point on the original function a over b, and when I reflect that over the line, it's going to end up on a corresponding point on the inverse, because that's how the inverse works. The question is, where is that point? Oh, sorry, Case, I didn't see.
You're gonna switch the B and the A.
So again, where's that point?
BA.
There you go. That's also an important concept that we need. The x and the y coordinates switch. Because y equals x, you switch the variables and you get to that. So if the point 2, negative 1 is on the original function, then the point negative 1, 2 is on the inverse. If the point 3, 4 is on the inverse, then the point 4, 3 is on the original function. Because again, we're reflecting over that line y equals x. So the derivative of the inverse function, which we'll do later when we get to the calculus, is you can do it, as I mentioned, two different ways. I'm going to stress with you the graphical approach to it because I think it's a lot easier, which we'll get to in a wee bit. That's what we just talked about. Beautiful. All right. I want to know if a function has an inverse function. And like I said, all functions have inverses. We're concerned about whether or not there's an inverse function. So we've already done something called the vertical line test. What's the vertical line test do, Kev? Or as we call it, the VLT.
It goes away.
No? Don't remember? Okay. No, yes. What's the vertical line test do?
There can't be 2 points in the same x coordinate.
Otherwise? What, oh, okay, yes. What's it testing?
It's like the line.
Right? And, okay, so let's suppose I draw a vertical line and it doesn't hit in 2 points. What does that tell you about the graph?
Is a function.
Bingo. Okay, we're testing whether or not it's a function. But we did that a long time ago.
Horizontal.
Yeah, I got it, Cam, thanks. With inverse functions, we're going to introduce something called the horizontal line test, which again, I think you did last year, yes? Okay, the horizontal line test, same concept. It can't hit the graph in more than one spot. And the reason is, or what it's going to test is whether or not the inverse is a function. And so if we go back to this picture, whoops, wrong way. If I go back to this picture, if I have a vertical line that I use to test the vertical line test with, if I reflect that vertical line over the line y equals x, all of a sudden it becomes a horizontal line. So what we're doing actually is a vertical line test for inverses. Vertical becomes horizontal when you reflect over y equals x. So the horizontal line test tests whether or not a function has an inverse function. That's why parabolas don't have inverse functions. They have inverses. You can find the inverse of x squared. It's just not a function. Make sense? Okay, good. Passes the vertical line test, x squared for instance, passes the vertical line test. It is a function, but its inverse is not a function because it doesn't pass the horizontal line test. There's the fancy schmancy stuff that says that. Okay. What does 1-to-1 mean? Okay. Oh. Christelle? What's 1-to-1 mean?
I don't know either, or I don't remember.
I understand. Allison? Any idea?
Is it where like one y value only has one x value?
Perfect. Yep. Every y value has only one x value. Every x value has only one y value. Good. And then number 2, what does strictly monotonic mean? Have you ever heard that term before? Didn't know if any of your pre-calc teachers were feeling fancies in their panties and threw that one out. It's pretty much a calculus term, but it does pop up occasionally, and maybe they used it. Strictly monotonic means it's always increasing and it's always decreasing. Yes, Cam?
So what about like the trig functions and like that dampening function that we did? Is it
Not strictly monotonic.
But is it for when you're taking the horizontal line test, you only do one period?
It depends on what you're testing.
To like find the inverse function of cosine. Even if
It doesn't have an inverse function.
oh, so
It has to be restricted on a domain. So you'll see when we start looking at the trig, which we will,
secant function.
it'll be restricted to a single period.
Oh,
The sine function, for instance, does not have an inverse function
because cosecant.
until you restrict it from 0 to 2 pi or
Okay.
pi to negative pi, negative pi to pi. Because it doesn't pass the horizontal line test. How would you check to see if a function is always increasing or always decreasing? Mary?
First derivative terms.
Keep going. You're right. First derivative, and then what? So just take the derivative and look at it?
And then do the line.
Yeah.
Or like
And what would I be looking for in order for it to be strictly monotonic?
if it's always increasing, it's decreasing.
Can I have critical numbers?
Yeah.
So as long as the function doesn't go down then up or up then down, it would be strictly monotonic. What if it goes down, then I get a critical point, then it goes down?
Then it's still decreasing.
Good. Could something weird happen at that point that would cause it to be not strictly Can you think of a graph where it would be decreasing, then a funky point where something weird happens, and then decreasing and not be strictly monotonic?
Maybe like cubic or some, or I don't know.
Okay, so if I go back to this picture, so if I go back, come on, there we go, almost there, there we go. This is a graph of a cubic. So something weird is gonna happen there on the first derivative number line, right? It's gonna be a critical number because the tangent line is horizontal. But this is increasing and increasing, but that point is weird. Are we okay? Is this strictly monotonic?
No.
No, it is. Yeah, sorry. I kind of baited you with that one, but yeah. That, as long as the graph matches the way you described it, that all the arrows are pointing down or all the arrows are pointing up, we're good to go. Get out your calculators, please. We'll test A using our calculator. So graph the function x cubed plus x minus 1 on your calculator, and tell me if you think it's inverse of the function.
I don't remember testing yesterday.
Holy smokes. Where's it, in the back of your car? Getting all frozen?
Probably.
Oh, my window.
Does it have an inverse function?
Yes.
Okay. While you have your calculators, check the second one too. Change the signs on the two things and see if it's also strictly monotonic. And then we'll confirm one of those with calculus. It's not? Okay, so let's do the one that's not. I don't care which one. Let's do the one that's not, just for giggles. We'll do B. F prime of x is 3x squared minus 1. Where's the critical number?
Plus or minus square root of 130.
Say again.
Plus or minus square root of 130.
Well done. Thought I could get you with plus or minus, but somebody had their wheeze this
Square
morning.
root over 100.
That's what I meant, yeah. Just see, that was another test. Good job. You passed that second one, so you guys are,
Take home test.
can't fool you guys.
Is that the take home test?
No, because you're not at home. Let's see, what if we put -2 in there? That's gonna be positive. Put 0 in there, we get negative,
Just end
and we're done.
it. End it there.
I can keep going, but now all of a sudden we know it's not strictly monotonic. And again, I keep saying this over and over again, but it's an important concept that I want to burn into your brains. It does have an inverse. I can take that function for part B and find the inverse function, or sorry, I said it wrong, there we go. I can find the inverse, but what we know with the calculus we just did is that that inverse is not a function. And you looked at the picture, right? What is the picture, man? Yeah, so it's got a little bit of more of a humpy thing in there that would prevent it from passing the horizontal line test. It's a word. Okay, yeah, so there's the first one, good to go, excellent. There's the graph you saw. This one, not so much, doesn't pass the horizontal line test, not one-to-one, all of those things wrapped up into one nice little picture. Okay, blah, 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 blah. All right. Fine, Now, how to find the inverse functions. So we've looked at, here's two functions are the inverses of each other. Here's a function, doesn't have an inverse function. Take the derivative, find the critical points, blah, blah, blah. But now, here's a function, what is its inverse, is what Cam was talking about earlier and what you did in pre-calc yesterday. Or yesterday.
Yes.
Wow. It seems like just yesterday. Okay. The new thing from pre-calc could be, we now know enough that you can confirm that it has a inverse function. I don't know if you did that last year using the horizontal line test, but now you've got two options, horizontal line test or the derivative like I just did. Switch x and y, solve for y. The resulting function is your inverse. Yes?
Are you really nitpicky about it that if you don't change the f of x to like a y at first, that, because I remember when we did that in like algebra 2, you would just get the whole problem wrong if you didn't change the f of x to a y. Do you not care about that?
I don't care about much. It's what the AP cares about.
Do they care about that?
They probably will, yeah. Notation is, they're very big on notation. If you're talking about f of x, then you gotta use f of x, but now when you start doing an inverse, where it's no longer f of x, it should be changed to the other variable, which I think I included here in my example.
Yeah.
Yeah, we mentioned that already, great, okay, where's my, here it is, alright. We'll start with that. Nice little square root function. Find the inverse of that bad boy. Excuse me. So I think I confirmed, yeah. So I did all the work early to confirm that it actually does have an inverse function. Whether or not you need to know that is dependent on how the problem is phrased. Notice this says find the inverse function. It doesn't just say find the inverse, it says find the inverse function. So I do need to confirm that it has an inverse function. There's the graph. Okay. Passes the horizontal line test, that's fine. Or I did the derivative. The derivative's always positive. Since the derivative's always positive, it's going to be always increasing no matter what the critical number is. And you can actually use that as a cheat there instead of doing the whole number line thing. Take the derivative. Is the derivative always positive or is the derivative always negative? If it is, then you're good to go. Okay. Then actually finding it. This is what you were talking about, Cam. Change f of x into y because we're going to start switching things. And then undo all those operations, which is really how you determine the inverse, is to use the inverse function. So it says square root, I'm going to square. Instead of subtracting, I'm going to add. And instead of multiplying, I'm going to divide. And we end up with, oh, I think I skipped that. Hold on. Thought I had it in the slideshow, but apparently I did not. Okay. 2x minus y is equal to y squared. 2x is equal to y squared plus 3. Therefore, x is equal to y squared plus 3 over 2. Switch them back, and the inverse of f of x is equal to x squared plus 3 over 2. Did I make a mistake?
No, the way I did it, I would switch the variables and solve for y, and you just solved in terms of x and then switched it, so that was part where I was confused.
Oh,
We
sorry,
usually do
yeah.
the work and then,
Yeah.
we switched and then did the work versus doing the work and then switching, so it just
My bad.
threw me.
Yep.
But either way works.
Same thing. I went out of order, I apologize. I failed you. If you're feeling fancies in your panties, you can verify it, put one into the other, then put the other into the other one. Okay, now some calculus. So theoretically, other than the phrase strictly monotonic, theoretically all of that should be reviewed. But now we want to start taking a derivative. There is a formula you can use, but I'm going to show you, aside from the formula, I'm also going to show you another approach, which I personally think is easier, but again, whatever one you want to use. So here's the formula. Two different phrases. There's the fancy schmancy calculus speak. I simplified it a little bit by because g of x sometimes confuses people if they don't read the first sentence, which I would guess many of you didn't read the first sentence, that g of x is the same thing as the inverse. So there's the formula. If you want to use the formula, great. So what is that saying? That's saying I've got a function f. I would like to know the derivative of the inverse function at a point x, or at a value of x. So you got to be a little sneaky about it, but eventually you can just plug and chug. Notice you got to find the inverse. So find the inverse of the function, plug in that x value, get a number, then take that number, put it into the derivative of the original function, then take the reciprocal. But I'm going to show you a different approach, which I think makes a little bit more sense. My approach is a graphical approach, and it requires that you remember a couple things. One is what we already talked about. If AB is on the function, then BA is on the inverse function. The more important thing to remember is that if I have a tangent line to the original function, then the corresponding tangent line on the inverse is a reciprocal. Not opposite reciprocal, that's a common mistake, just a reciprocal. In other words, if on the function I have a tangent line that has a slope of 2/3, then the corresponding tangent line on the inverse would have a slope of 3/2. And remember the slope of the tangent line is the same thing as the derivative, so that's a sneaky thing I'm going to use to get around that. Okay. So this is not a big deal, it's just trying to drill home what we already talked about, that if a point is on the function, its opposite point is on the inverse function. So without finding the inverse function, can I figure out what the y value of the inverse is when x equals 3? So could you solve this by finding it? Yes, I could go and find the inverse of that function, switch the x's and the y solve. That's not necessarily an easy thing to do here. And then plug in 3. But if we're crafty about it, we can be a little bit sneaky. This is the x value from the inverse. So if that's the x value from the inverse, it's the y value from the original function. So I would answer that question by setting this original function equal to 3. Does that statement make sense? Everybody? Yeah. Okay, so not only are we switching AB to BA, but we're switching XY to YX. So maybe I should write this down. So to find that y value, I'm actually looking for the x value of that. So I would take 3 and set it equal to 1/4 x cubed plus x minus 1. Well, that's not easy to solve. Good choice, Reedy. No. 4 equals 1. This isn't good. Oh, wait. It is good. It's 2. How did I do that?
He just did.
I just did. Yeah.
You saw
I knew it wasn't going to be anything ugly because that's not really solvable easily.
What's the difference?
8 times.
I just plug in 2.
Oh, I didn't even think of that.
Did you just plug in 2?
I just guessed, yeah. I figured it was probably either like 0, 1, 2, you know, that kind of stuff.
So how did you?
Okay, so magic. Literally, I just guessed.
There's a difference.
Hmm?
And you would find it, like if you put x cubed over 4 plus 4x over 4, multiply the 4 out, so it'd be 16 equals x cubed plus x, plus 4x, and then that's, yeah.
CCP.
Or just guess and get 2.
Yeah.
Or write the slideshow, know what the answer is.
Guess two.
But I didn't remember what the answer was. But I knew it had to be something pretty, otherwise it would just derail the whole problem. Which in fact, it's actually already derailed the whole problem, but we'll just pretend that we know what's going on.
Alright, I've got
which
this.
means that 2 comma 3 is on f of x. Therefore, to answer this question, 3 comma 2 is on the inverse. So we have to keep that straight. This was, make a little note here, this is f of x. This is the inverse of f of x. So now this. The problem with this is that we can't necessarily calculate f inverse of x. That's not an easy calculation to do. So if I want to plug and chug into the previous formula, I have to get a little sneaky about it. So I'm going to show you a different way to do it. I'm going to propose this. If I've got this function, whatever that looks like, it's some type of cubic, and I've got the 0.23 on that cubic, then when I take its inverse, I'm going to get this other point over here. That's the 0.32. My graph is way off, but you get the idea. Therefore, if I calculate the slope of the tangent line here,
Oh, that's me. Who is it, Mom?
I don't know.
What's the number on it?
Hello? Hi, Elizabeth. How are you? Elizabeth.
Spam.
Automated
Uh-huh.
voices.
Shut up. We're in.
We're in.
Okay, go ahead. Yeah, no problem. Go ahead.
Do we win a cruise?
She hung up on me. I got hung up on by a computer.
Do we win a cruise?
Well, yeah, we did. And then she said, we just want to tell you the details. And I said, yes. And then she said, well, thanks anyways, and hung up.
I think they just assume you'll say no at some point.
I didn't. I said yes. I'm sorry, Cam. I tried.
It's fine, it's fine.
Who knows where you could have gone?
Yeah, I could have gone to
Mediterranean, Caribbean,
Russia.
All right, where was I?
It's the tangent line.
Tangent line of that function is going to have a corresponding tangent line on the inverse. These two lines have reciprocal slopes. So this I can do no problem. That's easy peasy. Find the derivative, plug in 2, get a value, and then flip it over. Okay, so we need f prime.
They don't have parallels.
3/4 x squared plus 1. Plug in 2. Now why 2? Because again, we did the sneakiness here. We figured out if 3 is on the function, or on the inverse, then the point would be 3,2, and therefore the 0.23 would be its corresponding point. So we should get 4 is 4. And that's the slope of this tangent line here. And what we need is this slope here, and that would just be 1/4. They're just reciprocals of each other. If I can work out the point thing, find out where the point is on the function, the point is on the inverse, then I can get that inverse derivative by just using that information and a simple derivative of a function we're given.
Why'd you plug in?
Question.
Why'd you
My,
plug
my
Question.
question was, when you're taking the reciprocal, is there a way we should show that on our work, or how should that be done? You just do
To
it?
take a reciprocal,
Yeah,
just do it.
okay.
Can you take a reciprocal?
Yeah, I just didn't know what work we were supposed to show.
I don't think there is any work.
Yeah,
to
that's
show.
what confused me.
Okay. Yes?
Did you plug in 2 because it's 3/2 for the other point?
Mm-hmm.
Okay.
Does that make sense? Okay.
How'd you get this before?
Oh, I plugged in the 2 from this. So we did this first. I found out that that point on the inverse was 3,2. And if that point's 3,2, then the corresponding point on the original function is 2,3.
Oh, okay.
And if I want the slope here, it's going to correspond to the point here. Slope here. Found that slope, flipped it over, done. Okay. What do you got?
So is 4 the slope for f of x? Or?
Yeah. Good question. That's f of x. This is what we're looking for, which is f inverse prime of x. Or of 3, I should say. Okay? Good. Okay, blah, 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 okay, we did that already, beautiful, yep, Did I have the right answer, by the way? Yes, 1/4, good. That would be embarrassing. And then the red, like I said, remember it's a reciprocal, not an opposite reciprocal. Common mistake there, throw a minus sign in front of it, don't do that. I don't think we need to do this. I think you trust me, right? If you don't trust me, you can go back to the slideshow and work this out. But all this is doing is confirming what I've already said. The slope at the 0.24 would be the reciprocal of the slope at the 0.42, and we're good to go. Does anybody not believe me? Would be funny if I taught you wrong, but I didn't. We're done. Okay. This stuff is not on the quiz on Monday. On Tuesday. Tuesday is a non-calc